Hey everyone, welcome to this explainer. Today we're going to completely demystify the physics of spherical lenses. We're taking you on a journey, starting from basic physical shapes all the way to the elegant math that literally powers your everyday devices. You know, everything from the glasses on your face to the incredibly complex camera in your smartphone. I mean, have you ever just stopped and wondered about it? How can a simple curved piece of transparent glass take all this blurry, chaotic light bouncing around and organize it into a perfectly sharp photograph or, well, clear human vision? It honestly seems like magic, right? But it's not. It is pure, brilliant physics. And today we're going to decode exactly how that happens. So, here's our roadmap for today. We'll look at the two types of lenses, the rules for bending light, how lenses actually form images, formulas and lens magnification, and finally, lens power and combinations. Let's jump right in. Section 1, the two types of lenses. Okay, let's establish our two main players in the world of optics. First up, the convex lens. You'll notice it's thicker at the center, it kind of bulges outward. Its absolute superpower is converging light rays, literally grabbing them and bringing them together. Because of this, it's super versatile and can form both real and virtual images. Now contrast that with the concave lens. It's thinner at the center, curving inward, kind of like a cave, right? Instead of bringing light together, it diverges or spreads those light rays apart. That means it only ever forms virtual images. No exceptions. Now, it helps to think of every curved lens as just a tiny fragment of two intersecting spheres. Seriously, if you imagine extending the curves of any lens all the way around into full circles, you find our essential anchor points. The centers of those imaginary spheres are what we call the centers of curvature, labeled C1 and C2. And that straight line running perfectly through them, that's our principal axis. Right smack in the middle of everything is the absolute most critical point on our lens, the optical center, labeled with an O. Think of this as our 0 point. It's got a very special property. While the rest of the lens is busy bending light, a ray of light passing exactly through this optical center, it travels straight on through, totally undisturbed. Zero deviation. All right, moving on to Section 2, Rules for Bending Light. When you compare how these lenses bend light, the rules for drawing ray diagrams are actually pretty simple. For instance, a light ray traveling parallel to the principal axis behaves in a super predictable way. On our converging convex lens, it gets bent directly through the principal focus on the other side. But on the diverging concave lens, the ray gets pushed outward, so it only appears to be coming from the focus on the same side. Conversely, if a ray passes through the focus first, it pops out perfectly parallel to the axis on the other side. And like we just saw, a ray going straight through that optical center never bends at all. Let's officially define that incredibly important focal point. This point of convergence on a convex lens, or the point of apparent divergence on a concave lens, is called the principal focus. We label it with a capital F, and the physical distance from the optical center to this principal focus, that's the focal length, denoted by a lowercase f. Lock this measurement into your brain. It is the fundamental variable we're going to need for all our math a bit later on. Section 3, How Lenses Form Images. So the really crucial thing to remember is that a convex lens is insanely versatile. It creates completely different types of images depending entirely on where you place the object. If the object is super far away, at infinity, you get a highly diminished, real image perfectly pinned at the focus. But as you bring that object closer and closer to the lens, the real image moves further away and gets progressively larger. And here is the coolest part. If you move the object incredibly close, like between the focus and the optical center, the light rays actually can't converge on the other side. Instead, they form an enlarged, virtual, and upright image on the same side. This, right here, is exactly how a magnifying glass works. On the flip side, the rules for a concave lens are remarkably simple. It is so much more predictable. Because a concave lens always scatters or diverges light, it can literally never project a real image onto a screen. No matter where you put the object, whether it's out at infinity or right up against the glass, it only ever gives us virtual, erect, and diminished images. The image is always going to appear smaller, right side up, and floating somewhere between the focus and the optical center. Okay, Section 4, Formulas and Lens Magnification. Let's get into the math. Now, to do the math without getting utterly lost, we've got to establish the rules of the game. We follow a strict Cartesian sign convention. Just think of the optical center of the lens as your absolute origin point on a graph, 0, 0. Any distance measured to the right is positive, and any distance measured to the left is negative. Since light pretty much always travels from left to right, your object distance is almost always going to be a negative number. Oh, and any height measured upward from the principal axis is positive, while anything hanging below it is negative. Simple as that.
All of these rules build directly into the famous lens formula. This is a single, remarkably elegant equation tying the whole system together. 1 over v minus 1 over u equals 1 over f. So v is the distance to your image, u is the distance to your original object, and f is the focal length of the specific lens you're using. Armed with this formula and those strict sign conventions we just laid out, if you know just 2 of these variables, you can mathematically pinpoint the exact location of the third. No ray drawing required.
Finding where the image is located is awesome, but, we also kind of want to know how big it is. For that, we calculate magnification, represented by m. Magnification is basically just the ratio of the image height to the object height, which neatly corresponds to the ratio of the image distance v to the object distance u. The resulting number tells you everything. If m is greater than 1, your image is enlarged. If it's a fraction less than 1, it's diminished or shrunken. But you really have to pay attention to the sign. A positive magnification means you have a virtual upright image, but a negative value, that instantly tells us we are looking at a real inverted image, completely flipped upside down. And finally, Section 5, Lens Power and Combinations. Think about it. When you go to the optometrist, they don't prescribe you a focal length, right? They prescribe you a lens power. Power, represented by P, is essentially the bending muscle of a lens. It tells us the degree of convergence or divergence the lens can actually produce. Mathematically, it's super straightforward. It's just the reciprocal of the focal length. So a shorter focal length means a stronger, more extreme bend of light, which gives you a much higher power. The standard SI unit we use for this power is the diopter, represented by a capital D. But to make the math work properly, you absolutely must measure your focal length in meters. When you do that, 1 diopter perfectly equals 1 inverse meter of focal length. Put simply, a lens with a focal length of exactly 1 meter has a power of exactly 1 diopter. And because we mathematically locked in our sign conventions earlier, the power inherits those exact same signs. A converging convex lens, which has a positive focal length, will always pack a positive power. A diverging concave lens, with its virtual focal point residing on the negative side of our Cartesian plane, carries a negative power. So if your glasses prescription is a +2, you're wearing convex lenses. If it's a -2.5, you are rocking concave lenses. Now, here's where it gets incredibly practical. Why does a professional camera lens or high-end microscope have so many different pieces of glass shoved inside it? Well, because no single lens is perfect. By combining multiple lenses right in contact with each other, optical engineers can literally just add their positive and negative powers together algebraically. A +2 diopter lens combined with a -1 diopter lens results in a system with a net power of +1. This clever trick allows designers to drastically increase magnification, sharply improve focus, and expertly cancel out various optical defects and distortions that a single piece of glass would naturally create on its own. I really hope this explainer has clarified the fascinating physics happening right in front of your eyes. From the pure geometric shapes of intersecting spheres, to the rigid rules of bending light, straight into the practical formulas and combining powers, it is just a magnificent system. So the next time you grab a pair of binoculars, take a photograph, or even just put on your reading glasses, I want you to take a moment to ask yourself, how are these carefully engineered pieces of curved glass bending the invisible rays of light to completely shape your reality? Keep exploring, keep learning, and we'll see you in the next explainer.